Good day, ladies and gentlemen. Welcome to another edition of Prometheus University. We understand that it has been a while since our last video, but we promise to be more consistent with our output from now on. In this video, we'll be going over the basics of structural dynamics. It'll be the first part in a series of parts going over concepts in structural dynamics, and we'll be concentrating on stiffness and its relationship to undamped vibration. Now, as usual, what we do in these videos is to unpack the concepts by first starting with the words and then going to the intuition and then getting to the mathematical or analytical representations of these intuitions, coming up with formulas and wrapping it all up in a bow, if you will, so that we have a deeper understanding of these concepts, so that when we use them in our practice or in class, we have a better feel for what is going on. Okay, so if we dive right into it, what is this idea of structural dynamics? Structural dynamics is concerned with the response of a structure to dynamic loading. Let's unpack the term dynamic loading. Now, dynamic loading can be easily replaced with the word vibration. Vibration is something that we have an intuitive feel for. Okay, vibration changes with time. It is dynamic. There's a change in position with time, change in velocity and change in acceleration, and what have you. Now, what's the word response? Because I said response of a structure to dynamic loading, or response of a structure to vibration. The response that we're concerned with here are space-time responses, kinetics and kinematic responses. In other words, there's going to be a displacement. How far does it displace as a result of this vibration? There's going to be a velocity. What's the velocity of the vibration? What's the acceleration experienced as a result of the vibration? As a result of the displacement, the velocity and acceleration, they're also going to be stresses. Stresses due to just simple displacement, for example, and forces due to acceleration of the masses, for example. So when we talk about the response of a structure to vibration, we're talking about displacement, velocity, acceleration, and the consequent forces and stresses experienced by the structure. So one more time, we're concerned with the response of a structure to dynamic loading, and the loading being the forces and the stresses are dynamic because the vibration is dynamic. The displacement and the velocity and the acceleration have a time history. It changes with time, so the loading is going to change with time. It's going to oscillate, if you will. Now, there are a number of ways in which a structure can vibrate, in which you can introduce dynamic loading to a structure. But in this particular video, we're going to begin with the concept of undamped free vibration. We'll talk about what it is to be undamped in a second, but the concept of free vibration has the idea of natural frequency very closely tied to it. So we can talk about free vibration by talking about the concept of natural frequency. Natural frequency is something that we've heard before. We may have an intuitive feel for it, but just to put it in some formal terms, we could say that a natural frequency of a system is the frequency at which a system, and the system could be a pendulum, a guitar string, a tuning fork, a loaded spring, the frequency at which a system oscillates when not subjected to continuous or repeated external forces. So free vibration, which introduces the natural frequency, is the scenario where we take the pendulum, we displace it, and we let it go, and we don't keep pushing it. Okay? We pluck the guitar string, and we don't keep hitting the guitar string. We allow it to freely vibrate in accordance with its nature. Hence the term natural frequency. Now, a question that immediately arises to mind based on what we've said so far are what are the parameters? What are the parameters that make it such that guitar string A vibrates at a certain frequency, a certain number of oscillations per second, while guitar string B vibrates at another frequency? Why does this pendulum oscillate at one frequency and the other pendulum oscillate at a different frequency? Why does this loaded spring oscillate at one frequency, and so on and so forth, right? Now, for the case of a loaded spring or a guitar string or a pendulum, there are going to be different parameters involved, but there must be a set of parameters that we can represent analytically and generalize that can tell us what makes it such that one particular system vibrates at its natural frequency and another one at a different natural frequency. Now, a structure, a building of any kind is a system, can be idealized as a system with a natural frequency. And if we're concerned with the response of a structure to vibration, right, the natural frequency response is of course going to be of paramount importance to us in our modeling of the dynamic behavior in the terms of the displacement of the vibration, the velocity of the vibration, the acceleration of the vibration. The dynamic behavior of a structure, its natural frequency is going to be of paramount importance to us. And today's video, we're going to go ahead and derive from the model, from the way we model a structure, its natural frequency. What kind of a model do we use to represent a building? Now, let's start with a simple building, a simple single-story structure. It is represented with this lollipop here. It is an inverted pendulum shape with mass concentrated at the top. So we take the mass of the roof and half of the wall, let's say, and we concentrate it at the top. And then we take the stiffness of the column and we represent the stiffness of the column of the walls, and we represent it here with the typical stiffness representation K, and mass being represented by M. Now, what kind of motion will happen here? Okay, the motion is we will pull this at the top, and it's going to oscillate back and forth with 1 degree of freedom. So we're going to idealize it moving from left to right as shown with 1 degree of freedom. And this is the typical way in which we model a structure, starting with, again, just a simple one-story structure, or it can even be seen as one column with mass concentrated at the top. Now, we are going to start out by showing the formulas and then going about deriving them, because we might already be familiar with these formulas. We know that the period is the amount of time it takes for one oscillation. And we may have seen this formula saying that the period of the model which we just shown is equal to the square root of the mass divided by the stiffness. Now, the period is the reciprocal of the frequency, right? Because the period is the amount of time for one oscillation, and the frequency is the number of oscillations per second, okay? Frequency is number of oscillations per second. The period is the number of seconds for one oscillation, okay? So hence, the frequency would be the square root of K over M. So at this time, I would like to point out that the parameters being used and the form of the equation here is intuitive. In other words, we have a direct proportionality between the stiffness of the columns, the stiffness of the building frame, as it were, and the vibration. So we know that if we have a stiffer pole, a stiffer ruler, and we pull on it, it's going to vibrate faster. It's going to have a higher frequency. Also, we can imagine if we have a higher mass concentrated at the top, a massive mass concentrated at the top of the column, the frame, of the ruler, it's going to vibrate slower. It's going to have a smaller frequency. Hence, the parameters in this equation and the functional form make sense. Question might be, well, what's the square root business, and so on and so forth. Well, all that will become self-evident as we're going to go on to derive the equation. So as is typically the case with a lot of derivations and a lot of studies in the whole of mechanics in general, we look at things in terms of the kinetics and the kinematics. That is to say, we look at things in terms of the kinetics, which mean Newton's laws of motion, masses, accelerations, velocities, and forces. And then we also look at the system in terms of kinematics. Kinematics being just the graphical representation of the motion. The graphs and the polynomials, the formulas, the trigonometric representation, in this case, of the motion that we're looking at, or the system that we're looking at. And then we bring these two together and we can come up with something powerful that allows us to paint a nice picture of the space-time and mass and force behavior of a system. So that's exactly what we're going to do here. We're going to take this system and we're going to represent the stiffness in terms of the stiffness of a spring. So the diagram shown here is a red spring. That squiggly line is a red spring with K written on top to represent the stiffness of the spring. And then we have a block to which the spring is connected. This block has a mass M. That blue line represents the rest position of the spring. So the spring is neither stretched nor is it compressed. The spring, it's not stretched nor compressed. So the blue line is the line of equilibrium, if you will. Now, we're going to represent the free vibration. And by the way, there is no friction. So this oscillation will go on presumably forever. Hence the undamped vibration. We're studying stiffness and undamped vibration. So there's no energy loss, there's no friction. It is an idealized situation. We will introduce the concept of damping, which is fairly simple, which is just the loss of the energy over time, in the following videos. We're going to go ahead and we'll stretch out the spring a distance x. Now, in this idealized situation without friction, what will happen is the spring will then go back and compress an equal distance x in the other direction, and then it will continue to oscillate in this manner, going out from the neutral position x and back to the compressed position a distance x as well. So this is how we're representing our motion, and we're going to ask the kinetics questions. What can we talk about the forces and the masses and accelerations and so on and so forth? How do we apply Newton's laws of motions to this system? Well, basically we have a system of dynamic equilibrium, okay, in the sense that the mass and the acceleration, right, there's an acceleration going on the whole time. It's going to accelerate from the compressed position towards the neutral position, and then it's going to decelerate. In other words, the direction of the acceleration is going to change to the other direction, and it's going to slow down until it gets to stretched out to x again, and then it's going to go back, accelerating towards the compressed position, and then it's going to start decelerating once it passes the neutral line, which is represented by the blue line, right? And it'll keep on doing this. So we can imagine this, right? It accelerates to the blue line, starts decelerating, changes direction, accelerates to the blue line again, crosses that, starts decelerating. So this mass and acceleration, which gives us a force, has to equal to the force of the force in the spring, which is equal to the stiffness of the spring, which is given in force per distance, right, multiplied by the distance x. So the equation of dynamic equilibrium says ma is equal to kx. So now all we're doing here is stating that this system is in dynamic equilibrium, that its mass and acceleration has to equal to the X and the K force, right? The force due to its motion, which is produced by the stiffness in the spring, is equal to the force in the spring. So far so good. The concept of equilibrium is nothing too wild. We are familiar with that by now watching these videos. So what can we say about that then? We're going to say something about the acceleration because it's going to be useful to us. We're going to write down that the acceleration is equal to kx divided by m. Okay, so now we have a representation using the stiffness and the mass, and we can talk about something about the response, right? The response, the acceleration. Recall when we said that structural dynamics has to do with the response of a structure to vibration. The response we defined as space-time responses: displacement, velocity, acceleration, right? In this case, we're going to pick out the acceleration and we're going to say it is equal to kx over m, all simply by writing an equation of dynamic equilibrium. Okay, now we go over to the other side and we're going to represent the same system in terms of kinematics. Now recall that in kinematic representations, in kinematics, we're concerned with graphical representations of the motion that we're concerned with. Over on the left-hand side, in the kinetics, we did the laws of motion in terms of force, accelerations, masses. We did that representation. Now we're going to do a graphical representation of this motion in time. Now, a circle is a perfect way of representing cyclical events, right? And a vibration is a cyclical event in the sense that it starts from one position, goes over to another, and then comes back to the same position and keeps on doing this over and over and over again. We can easily represent this as going around in circles. Okay, we have an intuitive feel for that, and we have a language familiarity with that, and also in terms of trigonometry, we have a set of trigonometric functions associated with the circle with which we describe this kind of behavior. Now, the cosine curve is the perfect curve to represent this motion in time. The cosine curve starts from a position of 1, let's say, and 1 in this case we're going to call x. Our initial condition is condition x, represented by the middle diagram over on the left. The middle diagram on the left, where we have stretched out the spring to position x. Okay, we stretched out the spring with the mass on it to position x, and that is our beginning position. And hence we see on the vertical axis there that we're starting at position x. And then as time goes on, time represented on the horizontal axis, we see that this goes from x back towards the neutral position, right? The position of equilibrium, and then it goes down to negative x, and then it comes back up to the neutral position, and then passes that and goes up to x again, and then down, the way in which we've intuited before on the left-hand side. Now we're representing this in terms of a graphical representation using the cosine curve. Would you agree that this is a fair representation? Yes, I think so. And we have seen this kind of thing represent vibratory motion. We can understand, we have seen, for example, the vibrations of an earthquake, right, being represented with what at least looks like a series of sine curves or cosine curves, let's say. Now, the question is, we need an equation, because ultimately what we're here to do, just like with most derivations in mechanics, is we have a formula in terms of kinetics for acceleration. Now we want the same formula in terms of kinematics, in terms of graphical representation for acceleration as well. Bringing those two together will teach us something rather powerful. It always does. Okay, so now in order to come up with the acceleration, first of all, we have to define what we're doing here. We just said that is the cosine curve, but let's write it formally what we're doing. So the position, right, over in the vertical axis, which we're just going to call the big X axis for ease of representation here, since we're representing the motion of the spring, being stretched out to X and so on and so forth. The position, big X, is equal to the cosine of frequency times time. Okay, frequency times time, omega times time. Now, what's this frequency measured in? The frequency will be, in this case, again, recall, we're doing a graphical representation. This frequency will be in radians per second. Okay, so picture that circle, and this frequency is how quick is this clock hand circling through that circle in radians per second, right? And when you multiply that radians per second times any particular time t, you get a particular radian, and hence the plot of the position in the cosine curve. Okay, so hence at time 0, right, at time 0, we have the cosine being at position x, which is our initial position, our starting position, because cosine of 0 radians equal to 1, right, or initial position, or which is being defined as x in this case. So far, so good? Excellent. So to reiterate, we're doing a kinematic representation, which is a graphical representation using circular motion because it's a perfect representation of cyclic events. Using the cosine curve, starting at our initial position, the cosine curve starts at an initial position naturally, and we're saying that position x is equals to cosine times frequency times time, frequency measured in radians per second, how quickly does this particular cyclical event go around the circle, multiplied by a position in time, that'll give us a radian, and then that plots the position on this cosine curve. So now we have a perfect representation. So how do we go from position to acceleration? A little bit of calculus comes in. The derivative of position gives us velocity. And if you just brush up on your derivative, you'll see that derivative of this cosine omega times time is equal to omega sine omega time. Okay, and then to get to acceleration, we do the derivative of the velocity, and then we take out the omega again, and then we have omega twice now, so omega squared cosine omega time. Okay, so basically we did the derivative twice of the position which we plotted out based on the cosine curve, and we've come up with an equation for the acceleration. Okay, now there's something that we need to note here. Note that cosine omega time is both in the position and in the acceleration. So the position is cosine omega time. The acceleration is omega squared cosine omega time. So you can simply say that the acceleration is equal to omega squared times the position. So omega squared big X is the acceleration. Okay, now we have, in terms of kinetics, an equation that says the acceleration is equal to k times x over m, where k is the stiffness, x is the position, right, the stretched out position, and m is the mass. And then on the kinetics graphical side, we have that the acceleration is represented by omega squared x, right? So where x is the position and omega squared, well, omega is the frequency in terms of radians per second, frequency defined in terms of circular motion. Now, what we need to do is bring these two together because they both represent the same thing. They're both equal to each other. So we say kx over m equal omega squared x. We cancel out x from both sides. The position x apparently doesn't matter. It's on both sides. That can cancel out. And simply we can see that omega is equal to the square root of k over m. So that is how we come up with that funny formula that is introduced to you whenever you take a class in structural dynamics or looking at simple harmonic motion for springs and so on and so forth, where stiffness is involved. Any simple harmonic equation where stiffness is involved and the mass is involved, we say that the frequency is equal to the square root of the stiffness divided by the mass. Another way of saying that is that the period is equal to the square root of the mass divided by the stiffness. Recall the frequency and the period are reciprocals of each other. The period is the amount of time it takes for one oscillation, and the frequency is the number of oscillations per unit time. Okay, so with that, we've established one of the basic foundations in terms of conceptualizing, in terms of modeling the behavior of a structure in vibration. And that concept is its natural frequency. So again, remember, we're concerned with the response of a structure to vibration. Response being displacement, velocity, acceleration, and the consequent forces and stresses that are induced on that. So this particular kind of response in free undamped vibration, undamped meaning, well, it's idealized, there's no friction, this motion will continue forever. But dampening just means that we're going to have a situation where the motion is going to reduce over time. So we swing a pendulum and we know it doesn't go on forever as a result of friction and heat, energy loss, entropy then gets lost into the universe. That motion will reduce in its displacement over time until it comes to rest. But in this case, we're just looking at the equation without the damping. The equation without the damping is an idealized situation. So thank you very much, ladies and gentlemen. And in our next video, we'll get in deeper. We'll talk about modes of vibration. In this particular case, we haven't really talked about that concept. We just assumed a particular mode for a single degree of freedom motion for one Storey structure. But we're going to get deeper into what modes of vibration are and how they come into play when it comes to natural frequency and the response of the structure in terms of stresses and forces. Thank you very much again, and if you enjoyed this video, please go ahead and subscribe and share and leave a comment.